Hello everyone, I come from Hangzhou Dianzi University. This is our paper, Adaptive Semantic Attribute Decoupling for Precise Face Image Editing. Our research is how to have a precise editing effect on face images. Face image editing is giving a face image, generate a new face with target attribute. As shown in the figure above, we beautified and removed expressions on a face respectively. These have a wide range of application in the fields of social, entertainment, and controllable face tendencies. As you can see, this is a structure of generative adversarial network. Maybe you don't clearly know how it works, but it is not important. The point is many researchers train this model by adversarial laws to synthesize high-quality face images. We need to use the blue part, which map a random vector to a face image. In this way, what we want to do is edit this latent code to control the target attributes of output. At present, many methods modify the latent code by a control vector. For example, an article of CVPR 2020, interface scan uses a normal vector to modify the latent code. Imagine that in the latent space, one part synthesis female face, and the another part synthesis male face. There is a hyperplane can divide the latent space into two parts. In this way, you can move the latent codes along the normal vector. After cross the hyperplane, the attributes will be changed. Although most of the latent codes can achieve a good editing effect, but there are still the following challenges. A part of latent code's editing effect is insufficient, and there are entanglements between attributes. For example, as shown in the figure, the first column is the original image. Interface scan changed the expression when editing the gender, and didn't achieve the sufficient editing effect when adding smiling. Correspondingly, to solve those two problems, we propose two strategies. One is adaptive editing. We modified each latent code with independent control vector. The another one is content loss. We limited the degree of editing. Through combination of two strategies, we kept other attributes and the background unchanged. So, let me show you how do we do that. It is effective to use only one control vector to modify many latent codes, but there are still a part of latent code having a good effect. Therefore, we assume that the hyperplane is curved. Maybe use independent control vector to modify latent code is better. For example, the latent code Z1 along the M1 can cross the attribute boundary fastest. But for the Z2, the direction of M1 is not the optimal choice. Along N2 can cross attribute boundary faster, thereby modification is more accurate. In order to calculate control vector for each latent code, we introduce a decoder that takes the latent code as input to predict the corresponding control vector. This is the framework we predict the control vector. We use a fully connected network as our decoder. Its input is the latent code with 512 dimensions, and its output attribute control vector also with 512 dimensions. With the attribute control vector, we can modify the latent code just like this. If we input the modified latent code to the pre-trained generator, then this image should be without target attribute, and this image should be with target attributes. In order to train such a decoder, we continuously sample from the latent space and calculate the corresponding control vector, and then modify the latent code. For the purpose of evaluate whether the predict control vector can effectively control the target attribute, we propose the following loss function. The first one is content loss. We calculate the L2 norm distance before and after the image editing. We hope this is as small as possible, so that only the target area is edited as much as possible. The second one is the classification loss. We introduced a pre-trained attribute classifier to calculate the attribute score of the modified image. We expect that the score modified along the negative direction is low, and the score along the positive direction is high. We finally add 2 loss as our total loss. We continuously update the decoder parameters by backpropagation, so that the final control vector can be adaptively edit images. In order to evaluate the decoder we trained, we did the following experiments. This is the loss curve of a training decoder on 4 types of attributes. At the beginning of training, the decoder cannot predict effective control vector. The classification loss is high. After several iterations, the classification loss gradually converges, and the control vector has a good control effect. Correspondingly, due to the modification of the image, the content loss increased at the beginning, and eventually turned to a small value. We know that a small period of increase in the middle of classification loss is corresponding to the period of decrease in the middle of content loss. It should be a trade-off between the attribute modification and the reduction of content loss by the decoder. In order to observe the editing effect on the different training stage, we use the control vector at the different iterations to modify the latent codes. The results are shown in the figure on the right. In 0 iterations, we can see that there is basically no control effect at the beginning. In 100 iterations, it has some control effect and high content loss. For example, when child age glasses were added. In 500 iterations, decoder trades off between the classification loss and the content loss. In 2000 iterations, both classification loss and the content loss was balanced and close to a small value. Here is our final editing result. As shown in the figure, edit the target attribute or remove the target attribute our method can achieve the good effect. To visualize the revision part, we calculate the ratio of image before and after the editing. From the figure, our method basically focuses on the area of target attributes. For example, when we edit smiling, it mainly changes the area of mouth. When we change the age, it mainly adds some wrinkles. We try to extract a control vector on two mainstream generators and evaluate the success rate of attribute editing. Firstly, we randomly sample 5,000 latent codes, the attribute distribution as shown in the table 1. We then use the unit control vector to modify the latent code with the attribute score less than 0.5 for add target attributes and record the number of success. The final success rate is shown in the table 2. Compared with all latent codes modified by one normal vector, ours can find a more suitable control vector to make the target attribute editing faster and improve the success rate of attribute editing. In general, we introduce a decoder to predict independent control vector for each latent code. We can better keep other attributes and the background unchanged when editing target attribute. Our method can edit the target attribute faster and has a higher editing success rate. Thank you for your attention.